Present some work I've been doing together with Michael Siegel on volcanic forcing and reconstructions, but I wanted to just quickly say thank you to all our attendees yesterday at our VICS working group, our second workshop, which took part here in Zaragoza. So a big thank you to all the participants who were there. A little tiny bit extra special thank you to our 5 keynote speakers who did a really great job stimulating our minds and our discussions. The local organizers, I don't know if Anna or Fernando were here, but they were great. And all the volunteers that raised their hands yesterday and volunteered to push forward some products, some case studies we're going to do as part of the VICS working group. So thank you, everyone. And if you're in this room and you're interested in volcanoes and climate, we are the VICS working group. Check out our website or the page on the page's website. There's a link to the mailing list, and you can keep informed through the mailing list and get involved. Okay, so what I'm going to present today. So one of the main reasons, I think, for looking at the proxy record is to try and understand what parts of climate variability are response to external forcing and what is due to internal climate variability. So here's an iconic figure from the last IPCC report based on paleo records and climate models. So the blue and red lines are climate model ensemble means of climate model simulations. The red and blue are different solar forcing, so you don't have to worry too much about them. And the gray shading is showing sort of probability distribution of different proxy records. And if you look at this comparison between models and proxies and do some formal detection and attribution kind of analysis on it, you can see that there's really good agreement between the models and the proxies largely because of the accuracy of the volcanic forcing over this time period. And some studies have shown that up to 50% of decadal variance from the 1400s to pre-industrial, so sort of 1850 kind of time period, is caused by or forced by volcanic eruptions. But that good agreement, that kind of detection, that attribution breaks down as you go back further in time. And of course, a lot of that is probably due to the proxies. As you go back, you're losing a lot of good proxy information, and the spread is getting wider. But I think there's a good point to be made that our understanding of the volcanic forcing was also suffering when these studies were put together. And in the last couple of years, so Michael Siegel and Joe McConnell and colleagues have been really pushing forward and doing a lot of great work, really clarifying the history of volcanic eruptions going back over the full last 2,000 years and even further. So now this is quickly becoming a standout paper from Michael in 2015, where he was able to absolutely calibrate or fix the dating of volcanic eruptions in the early part of the Common Era due to coexisting signals cosmogenic signals in the ice cores and in tree rings. So by fixing these dates, we were able to see a lot better correlation between the ice core dates showing sulfate peaks and the cooling signals in tree rings. So here's a little composite that he showed, a superimposed epoch analysis, where you look at the tree ring growth anomalies with respect to the years relative to the ice core sulfate signals. And before and after 1250, where we seem to have this break, now we see really consistent cooling in the tree ring records when you composite based on the ice core sulfate records. So we really think that this history of volcanic forcing in the past is much better than previous. But there are other issues, and if you're going to use this kind of history in climate models, you have to be a bit careful about how you put it into climate models. And so in this paper from De Vita Zanchetin in GMD, we saw that even when the volcanic forcing should have been pretty similar in all sorts of different climate models, what actually came out of the climate models, if you quantified the top of atmosphere clear sky net radiative flux, so something like radiative forcing, different models were all over the map. And part of that is because the forcing files which were provided in the last PMEP round, PMEP 3, took very different forms. And so one recommended forcing from Crowley and Unterman, so the ICI forcing, took the form of aerosol optical depth, also effective radius, whereas the IVI2 from Gao et al. In 2008 took aerosol mass. And in both cases, modelers had to make some assumptions and do a little finagling to get that into their climate model, probably leading to a lot of these differences. So the goals of Evolve 2K were to take these improved proxy records of volcanic activity from the ice cores, estimate volcanic stratospheric sulfur injections, so the amount of sulfur which was injected into the stratosphere by these eruptions. And the reason that we stop at this point is because this is directly ingestible by new interactive stratospheric aerosol models, so the kind of climate models that can actually simulate the evolution, the formation and evolution of aerosols. This is what they want, just the amount of sulfur, and then they can run their model. But a number of other models will need the full field optical properties for climate models. So what Evolve2K then produces the full field properties in the same format as the CMIP6 historical simulations, or historical forcing. So how do we do that? So starting from the ice cores, we're going to scale the ice core sulfate flux to this VSSI. And we do that in a manner very similar to Gao et al. In 2007, 2008, which was pioneered by Clausen and Hammer back in the late 80s and 90s. And so this volcanic stratospheric sulfur injection, VSSI, which I call M of S because I try and keep everything in terms of mass of sulfur, is proportional to these ice sheet average sulfate fluxes to Antarctica and Greenland, and then multiplied by these transfer functions, which account for the non-uniform deposition to the surface of the Earth of this sulfate. And there are estimates of these kind of transfer functions by nuclear weapons testing and from Pinatubo. And so we're using this value of 1 times 10 to the 9 kilometers squared, which is numerically the same as what Gao et al. Used in 2007, 2008. Although we have a slight change in interpretation, which leads to an effective 33% increase, which is sizable. But in the end, when you combine that increase with changes in the ice cores based on Michael's new compilations and what Gao et al. Used in the past, we actually see, in many cases, pretty similar results. So this is a comparison. Our new Evolve VSSI estimates are on the y-axis. The Gao et al. Or IVI2 is on the x-axis. And so you can see for the really big events like Samalas, Tambora, and Laki, we're really close to the 1-to-1 line. Generally within about 10% for those events. Excuse my crude PowerPoint lines here, but here we see a shift. So this big eruption, which IVI2 had in 1453, we have a shift by a few years to 1458, but the magnitudes of those two signals are really close together, which might be a little bit of luck. But then, of course, you see some other features. There's a number of eruptions definitely most earlier in the time series, which are much stronger in the new Evolve2K reconstruction. We're pretty confident that this is real. And then a lot of kind of moderate events, which are significantly stronger in Evolve2K. So this is a combination of different effects. Partially this 33% increase in the scaling factor, also better synchronization of the ice cores early in the time record. So that's what it looks like. Now these sulfur injections as a function of time going back compared with the IVI2. So things are pretty similar for the last 500 years or so. Then it starts to diverge a little bit around 1250 in terms of the timing and sometimes the magnitudes. During 500 to 1000, the history is quite different. And then, of course, our new reconstruction goes all the way back to 500 BC. So the next part of the chain is then to take those sulfur injections and produce optical properties. Mostly for, my reasoning was always thinking about climate models, but I think these are also interesting for other people who are interested maybe in what were the optical properties, the AOD, the radiative forcing in a particular area of Earth. So if you're looking at the high latitudes or something like that. So the way we do that is through this easy volcanic aerosol. It's a little module that I developed with colleagues in Hamburg. And it's a really, really simple little tool based on parameterized 3-box model of stratospheric transport and some simple scaling relationships. It takes this VSSI, some estimate of the latitude of the eruption, and optionally the hemispheric asymmetry of the aerosol spread, which you can get from the ice cores, and outputs, as I said, this what the climate models need. So aerosol extinction, if you take the vertical integral of that, you get the stratospheric aerosol optical depth, which is what I show on a lot of plots. But then also these other factors, single scattering albedo, asymmetry fraction, and all of these as a function of height, latitude, and wavelength. So I tried to get everything on one plot, which is kind of hard to do, but it's kind of a neat plot. So we show as a function of, every little panel is a function of latitude and the vertical and time for all the centuries and then all the decades. So you can pick your favorite century. I like the 6th century here, and here you see this, the double 536, 540. another good one back in 574. Yeah, so that's kind of a fun plot. Comparing it to the Crowley data set, so the latest version, Crowley and Unterman 2013, again, we see pretty reasonable agreement for the major eruptions. So there's Somalis 1257. We're very similar in terms of the AOD. Slightly surprising, and a little bit, it might be what many people might be interested in. Our Tambora is about 25% less than what was in Crowley at all. Even though our VSSI is, or yeah, the sulfur injection was completely consistent with Gao et al. And again, okay, so this kind of, we have then this main sequence of eruptions, which is very similar in the two data sets, but we have more of these stronger kind of moderate eruptions. And a lot of this, again, is due to better synchronization in the early time record. Yeah. And also, we're not scaling examples like Lackey, we're not scaling it down like Crowley did. We're going to wait until we have objective information in order to decrease these estimates. Our reconstruction overlaps with the CMIP-6 historical forcing for 50 years, so it gives us a chance to look at, say, Krakatoa, and we're very, very similar with CMIP-6 in terms of our aerosol optical depth there. Also a note, the new CMIP-6 historical forcing includes a background, so a non-zero background forcing, which Crowley did not. So Crowley would go to 0 if there was no eruption, but we go to something a little bit less, or a little bit more than 0, sorry, and it's consistent with the CMIP-6. So you can nicely run from our reconstruction into the CMIP-6 historical forcing, and there's no big changes. I'm going to skip ahead to this. Another thing that we've put some effort into, and I think is pretty important, is including uncertainties on our estimates. And so the main thing we did was calculate or estimate the random error in our VSSI estimates. And this is based on the estimated uncertainties in the ice sheet average sulfate, so basically looking at the variation of the different ice cores, and also folding in some representativeness error. Antarctica, the deposition to Antarctica and Greenland is a small proportion of the deposition all over the globe, and you need to understand that depending on meteorological conditions and so forth, it won't give you the exact, there's some uncertainty related to that. And we based that on model results from a study in 2013, and this is what our uncertainties look like. For most of the larger events, it's something between 20 and 40%, which seems kind of reasonable to me, but although we can look at it more in the future, of course. And so then you can start to think about what the uncertainties are in the AOD for different events, which allows you to, I think, more properly compare, say, different events. Was this event really stronger than another event, or could they have been the other way around? Better assessment of apparent mismatches between forcing and response, so a comparison with tree rings, and also allows for the construction of forcing ensembles, which I think is something interesting to look forward to. So, in conclusion, so our new Evolve 2K reconstruction provides estimates of the sulfur injections and aerosol optical depth from 500 BC to 1900. Then the largest events are in reasonable agreement with past reconstructions, but before 1250, things are a little bit different, and we're pretty confident that the Evolve 2K is more accurate than prior reconstructions. And these estimates all come along with uncertainty estimates, which I think is pretty important and will help us understand differences between models and proxies. Evolve 2K is the recommended forcing for PMIP4, so the next round for the past 1,000 and 2K experiments, and so I'm hopeful that this more accurate volcanic forcing will allow for better understanding of the role of volcanism and climate variability, going all the way back to 500 BC. So I'm waiting for a DOI. This is all up on a server. As soon as the DOI is, then I can go through with the actual submission to Earth System Science data, so it should be available for people to look at and comment on very, very soon. So keep your eyes open for it. Thank you. I can take questions.
I'd like to take this moment to thank my co-authors and my funders, as well as the VICS Pages Working Group. We had a great workshop yesterday, and it's been a really fun to be part of. So today I'll be talking to you about reconstructing stratospheric eruptions using high-resolution sulfur isotopes from ice cores. And as we had this nice introduction by Matthew just earlier, our best record of volcanic forcing of climate over the recent past comes from sulfate concentration in ice cores. So this is a plot from the Siegel et al. 2015 paper, where we've got time and sulfur concentration, both in Greenland and in Antarctica. And then this green curve here is a tree ring compilation of northern hemisphere temperature. And so volcanoes are emitting sulfur dioxide, which gets oxidized, deposited in the ice sheets, and so each of these events is a volcanic eruption. You can then scale the sulfate concentration, as Matthew just described, to a radiative forcing in watts per meter squared, or an optical depth, and use that to put into your climate models. And the key thing with these records is that you use the presence of a peak in both the northern hemisphere and then the southern hemisphere to identify what we call a bipolar eruption or stratospheric eruption, because if you have aerosols in both hemispheres, it suggests that the plume made it up to the stratosphere and thus was able to be transported globally. And this has really been improved, as Matthew mentioned, by the improved age model over this time period, and so this is a really nice record. There are a few complications, though, when you're just looking at sulfate concentration. So in the first instance, this sulfate concentration is very spatially variable, due in part to differences in accumulation rates. So this is an example from Lockheed, looking at concentrations in the ice at various ice cores in Greenland. The other difficulty is that you can imagine that ice core in Greenland is going to be really sensitive to any eruptions, for instance, in Iceland, just because of the proximity of that core. And so distinguishing between these local eruptions and the large stratospheric eruptions is going to be really important when trying to understand the effect of volcanoes on climate. The other thing is that this really relies on a great age model, which these cores do now have. But you need to be able to distinguish between a true bipolar event and from two distinct eruptions, so a local eruption or a high latitude eruption in the northern hemisphere that's within age dating uncertainty of an eruption that you see in the southern hemisphere. And so we want to improve on this by using sulfur isotopes, which allow us to fingerprint stratospheric eruptions, and by that I mean eruptions that make it above the ozone layer in the atmosphere. And the reason why we can do this is because UV radiation imparts a really interesting mass-independent signature to sulfur aerosols. And so if the volcanic plume makes it above the ozone, so it's no longer being shielded from UV radiation, you get a fractionation, a mass-independent fractionation in your sulfur isotopes. And so I'm going to be denoting that with this cap delta 33S. And when that is not equal to 0, we interpret that as being stratospheric. So it has interacted with UV radiation above the ozone layer. And this allows us to distinguish between these really climatically important stratospheric volcanoes from more local sulfate deposition from, for instance, Iceland, that was transported just through the troposphere onto the ice sheet, which would have a cap delta 33 of 0, so no mass-independent fractionation. This was pioneered about a decade ago by Melanie Baroni and Joel Savarino's group, where they looked at sulfur isotopes from two known stratospheric eruptions, Pinatubo and Agung. And these were measured from an Antarctic snow pit. And so what we're plotting here, so time is going in this direction, and these open circles are the cap delta 33, which is plotted here on this axis, with this is the 0 non-mass independent fractionation. And then these black symbols are the concentration of sulfate. So you see the eruption event, and you see this evolution from a positive mass-independent fractionation down to a negative mass-independent fractionation over this time period. This is really exciting because it really highlights the utility of this in being able to distinguish these, the sulfur that has been transported through the stratosphere. Now, these measurements were made on using gas source ICPM, or gas source mass spectrometer, which requires a lot of sample, and so that's why they used a snow pit. So they had a lot of material to work with. When you go back further in time and you're relying on ice cores, using traditional methods, you would need to use the whole peak to get enough sulfur to make a measurement. And you can imagine that if you are combining the whole peak, you could get a value of 0 because you're averaging positive with negative, even if it was stratospheric. And so it could be an inconclusive result, which is why I've been developing a method of reducing sample size requirements for sulfur isotopes. So this is a photo of my new lab at St. Andrews. And so this method of using sulfur isotopes uses a multi-collector ICP-MS. We have similar precision, 0.1 per mil precision to traditional gas source measurements. But the key thing is that we've reduced sample size requirements by about a factor of 1,000. So instead of requiring about months or years of ice accumulation, I can get down to about bi-monthly resolution, and I'm actually only measuring it on the wings of ice cores, so just the scraps that are left over after other measurements. So it's a very sample, precious method. So without further ado, I want to show some case studies that really highlight the utility of this method. So in the first instance, I want to look at this very large eruption, two very large eruptions, or one very large eruption around this 430 BC. So you can see here is dated at 426 BC in the Greenland neem core, and at 430 BC in Antarctica. And so the question is this one single stratospheric eruption, or is it actually two separate tropospheric eruptions that happen within age dating uncertainty of these two cores? So this is a plot of the sulfur concentration from the Antarctic core, showing that big eruptive peak. And then this is that cap delta 33S showing the stratospheric signal, where you, prior to the event, were within uncertainty of 0, so it's mass dependent, and then you see this characteristic positive down to negative mass independent fractionation, suggesting that indeed this was a stratospheric eruption, and that those two events that were dating within uncertainty of each other were actually the same event. And that's really important when thinking about the forcing, because if you interpret that as two separate events, they would be scaled differently than if it was one large stratospheric eruption. And this is important for then interpreting the tree ring records, which also shows a pronounced cooling at this time. Okay, so moving on to another really interesting case study, I'd like to finish off with this, this pair of eruptions in 536 and 540 Common Era. This is a really interesting time period from a historical perspective. So if you look through literature, you can get some great quotes. For instance, during this year, a most dread portent took place, for the sun gave forth its light without brightness, and it seemed exceedingly like the sun in eclipse, for the beams it shed were not clear. So this time period in 536, there was widespread cool climates in Europe. There was a lot of crop failure, massive famines, and then in 541, there's the breakout of the Justinian plague. So it's really an unpleasant time to be around. And we have these two eruptions identified in Greenland, one dated at 536 and one dated at 540. Now, what's particularly interesting about these is that one's much larger than the other in terms of sulfur concentration, and in Antarctica, there's just one peak. So the question is, well, which one is the bipolar eruption? The age model uncertainty is approximately 4 years, and so depending on which one you choose, you would get a different radiative forcing because of the different sulfate concentrations. Now, if you look at the tree ring records, what you see is a really strong decrease in temperature at 536, which might suggest that this really large one is the bipolar eruption. And so we measured sulfur isotopes, and Michael, in his paper, suggested it was this one, and it turns out he was right. So the moral of the story is Michael's right. And what we see is that this is the concentration, again, from Greenland, and this is the mass independent fractionation, this cap delta 33. And we see this characteristic positive going down to negative on 540. What's really interesting is actually we also see a stratospheric signal on this, this first eruption in 536, but we don't see a peak as well in Antarctica, which suggests that this is a high latitude stratospheric eruption. So these two different eruptions have very different shapes in both concentration and in isotope space. So we see this really pronounced mass independent fractionation, and we see a very diffuse sulfate peak. And so that is suggesting that that the sulfate that was deposited in Greenland was from a tropical eruption because it had long enough to impart a large fractionation, and it was deposited diffusely over a long period of time. In contrast, when we look at this eruption, it's a much more muted mass-independent fractionation and a really distinct sharp peak. Furthermore, nice work by Jill Plunkett in the Sigel et al. 2015 paper looked at tephra from this eruption and suggests a North American source for this volcano. So it's a northern hemisphere stratospheric eruption. And so this really highlights the potential of this technique to pick out climatically important stratospheric eruptions that you wouldn't necessarily get in a bipolar test because there's not a corresponding peak in Antarctica. You can take this even a little step further, and you can use isotope mass balance. So this is new work that I've been working on recently. And so you can use isotope mass balance of the minor isotope ratios to constrain the proportion of stratospheric sulfate, so this fraction of stratospheric sulfate, which you can then multiply by the concentration to give you an estimate of how much of that northern hemisphere stratospheric eruption was actually stratospheric relative to the stuff that was transported directly through the troposphere. And so this can then be fed back into the radiative forcing models that Matthew was talking about to try and improve our estimates of this forcing of climate through time. And then finally, new results as well. So I've replicated that this same eruption from Antarctica, so those are plotted in these red squares here. There's beautiful agreement, which is very satisfying, showing that the isotope signature is not affected by transport, so you're getting the same isotope signature in both hemispheres. And this is highlights a real potential of this method to really improve chronologies from Greenland and Antarctica on specific events by using this as an even more specific fingerprint. So to sum up, high-resolution sulfur isotopes in ice can successfully distinguish between tropospheric and stratospheric eruptions, including for these high-latitude volcanoes, like the 536 eruption. It improves our confidence in intra-hemispheric ice core chronology, and we can use isotope mass balance to distinguish the stratospheric sulfate from tropospheric sulfate. Thank you.
For high-latitude eruptions, your technique requires that the plume gets above the ozone, right? So what you call stratospheric what you call tropospheric might still be in the stratosphere.
That's correct. So, but in this case, because it was stratospheric, it means it gets even higher into the stratosphere. So it puts a sort of lower limit on the plume height. Yep, that's correct. Oh, with the isotopes? Oh, you know, that's an interesting. I haven't actually thought about that. Potentially, you'd probably want some higher resolution on the more recent eruptions that we know well to sort of calibrate that to actually see when you see that initial change.
Hi, thanks a lot. Allegra is extremely sorry that she can't be here. She had a bit of a family emergency. I know she was really looking forward to being here. Fortunately, I am, so I'm going to give her a talk. If there's anything you don't understand, blame me because of the translation. And if you have any further questions, obviously, just email her directly. There may have been more stuff that she wanted to add in that she was going to talk through. Obviously, I don't know what that is, so I'm going to try and do my best. And I apologize for the slight mismatch. Okay, so we're talking very much about how aerosols are being deposited. We're trying to infer from that deposition of aerosols what the volcanic forcing and aerosol optical depth processes are. But of course, we also know that the means by which aerosols are transported to the ice cores are in themselves climate dependent, right? So the processes that take an aerosol from an eruption site through the stratosphere, processes it chemistry-wise, deposits it on the ice cores are also, of course, modulated by the climate that you have at that point. So as climate changes, the pathways may change, the processing may change, and of course, because the volcanoes themselves are having a direct impact on the climate, there is a possibility that the volcanoes go off, they change the climate, and they change where things are being deposited by themselves, right? So we have to. It might not be a huge impact, obviously, and we have a lot of robust results anyway, but it is something that as we're getting to more of a detailed, process-orientated view of how to infer the climate response from these records, we start to need to think about. So we've done work historically on how climate changes themselves change, for instance, deposition pathways of aerosols in Greenland. This is a picture of both. So here we go. This is from Lagrangian et al. 2006, which was a study on how freshwater forcing changes the overturning stream function in the North Atlantic, and by changing the stream function in the North Atlantic, it created a regional cooling, and that regional cooling led to changes in the ice cores of both methane. So this is a decrease in methane because of that regional cooling, but also in aerosol species. So this is beryllium-10, which we were tracking because of our interest in solar forcing, and this is dust. So in both of these situations, the cooling that you saw in the North Atlantic gave rise to an increased concentration of aerosol in the ice core location in the model. So we have examples where large climate changes can influence the transport of aerosol species to the ice core sites. And so the question you might want to ask is, well, can we go a little bit further with that? So I'm going to show you some work from the last millennium ensemble that we did with for PMIP3 using the GIS model ER. The volcanic forcing is the Cardiff Unterman or GAU, land use changes, solar changes, greenhouse gas changes. It was a pretty standard CMIP5 set of experiments, except that we had water isotopes everywhere in the hydrological cycle, and we've been working on these vapor source distribution tracers to help work out what the processes are by which things get deposited. So this is a picture of the different forcings that you've seen before, and this is the ensemble of all the different models. And so you can see very clearly that the only big things that you can see, as Andrew Scherer has pointed out, and as was pointed out earlier on, are the volcanoes, until you get to the modern period when the greenhouse gas signal really comes into play. If you try and do epoch analyses of the volcanic signal in these simulations, you can, of course, do that, and you can find, if you do that, this is the 20 largest volcanoes, and you get this very nice clear cooling trend, a little bit different in different hemispheres. You can see changes in rainfall, and you can see changes also in the O18 of precipitation, which, if you're looking at the ice cores or a speleothem record, you might be interested in. So there are clear impacts on global scale metrics. So how far down do you need to go before you can pick out a volcanic signal at the local level? It's very hard at the local level because there's so much noise. But you can, I don't know why it's done that. The interesting razor blade effect is brand new to this computer. I'm not quite sure why it's doing this, but anyway. But if you look at Greenland as a whole, South America as a whole, Europe as a whole, and these are O18 and precip superposed epoch analyses, you can see in most of them. Sorry, something weird is happening there. You can see in most of them that there is an O18 signal that you can see that is associated with the volcanoes, but it has to be at a continental scale, unfortunately. So let me very briefly give you an idea about what we're doing with vapor source distributions. So vapor source is the idea of where does water come from, right? So where does it evaporate and where does it deposit, and how much of what's the footprint of the water that gets to wherever it goes. And so you can do this in a number of different ways. There's 3 different ways. Here's the way that people used to do it. Basically, you draw boxes, and then you paint the water. So box number 1 is red water, box number 2 is blue water, and then you just trace the average color as you go through the thing. Now, the problem with doing it this way is that you have to predefine your locations of interest. So you have to predefine what the North Atlantic looks like, what the Triple Atlantic is, and you have no specificity. So once you've done the run, then you're done. And so, it's all a little bit ad hoc and a little bit arbitrary, though obviously this goes back 20, 30 years, and it's obviously been very interesting, but it is somewhat limited in what it can do. You can also take models and then kind of put them through another model that traces Lagrangian trajectories. So this is an example of that. This is from, I can't remember his first name, Henrik Soderman? Anyway, Soderman in 2008, where he's looking at the back trajectories from Summit using an MCIM, which is an intermediate complexity model, to kind of back out where the water came from that was deposited on Summit for a particular period. So this is very good. You can have a lot of high resolution, but it's limited in terms of how far you can go back, and you have to assume that there's very little recycling along the way. So that's good, but limited. And so what we've done here is something else entirely. So we've set up what are called vapor source distribution, VSD tracers, which are spherical harmonics that we're imposing on top of the model. So each tracer is one spherical harmonic, and because they're orthogonal, you can put them all together again post hoc. And so you get an effective resolution of about T31, for anybody who knows what that is, but it's about 8 by 10 resolution, kind of smooth in spherical harmonic space. It's about 144 tracers that you work. It's very efficient computationally. All these tracers are independent. And the interesting thing is that you don't have to make any a priori assumptions about what you're interested in. And so you you run this, and then you can just go and ask any particular point, any particular region, where did the water come from, and it will return that estimate for you. So, for instance, here's an example for the modern period. This is what you get when you ask where does the water from Greenland come from in the annual average, and as you might expect, it mostly comes from the local North Atlantic, but also there's quite a big chunk of stuff from the kind of mid-latitude Atlantic as well. And this is where, and then you can see there's some local recycling, so stuff that lands on Greenland and then is evaporated from Greenland and then lands on Greenland again. If you look at the seasonal variation, so the difference between winter precipitation and summer precipitation, you can see something quite interesting as well. So obviously you get more, so this is DJF minus JJA, the red is where you're getting more summer evaporation. So obviously during the summertime you get a lot more continental evaporation and local evaporation from the Labrador Sea and a little bit less from the North Atlantic. And so there's a clear seasonal variation in where water comes from. And now you look at it for an eruption, right? So we did a composite analysis for the periods when we had big eruptions. And you say, during the years after an eruption, does the water come from different places than it did in other years? And the answer is yes, it does. So what you see is this period, 2 years past Pinatubo and Chichun, compared to the normal things. And so what we're seeing here is a reduction of evaporation and sources from North America and from Labrador because it was colder, and so things have moved to the south. So let me just wrap up, and again I apologize for probably not doing this talk the justice that it deserved. We think that there is going to be evidence that there will be significant variations, so there is evidence there are significant variations in moisture sources due to the instant application of a volcanic forcing. To see how that's going to impact volcanic aerosols, we need, and we are doing, better forward models for volcanic aerosols within the climate models so that the transport of the aerosols and the climate changes are all being included at the same time. And we hope to be able to use that to better infer what you should be thinking about for the forcings and the history from the ice core records themselves. So thank you very much.
So what would be, if we have three running models, so not just to specific meteorological situation?
Right. So we did the nudge runs so that people wouldn't say, oh, it was just because of something happened in our free running models. Maybe the response was incorrect. So we did the nudging runs so that we got the right phasing of the AO and the NAO with respect to those particular things. When you look at it in the free running cases, you have more variation in things like the NAO. So you need to take a bigger average in order to get the same level of significance per dynamic changes that you might want to look at. So the same signal is there. The nudging doesn't change the basic dynamics. It just changes the timing of things.
Doesn't it mean that it could be, if you have a different phase of the let's see, the armor or in a different ensemble state, that you get a different signal in the model?
Right. So we know that you would get a different signal if you had a very different AMOC state. You do see a very clear shift because of that, and then the modulation of that will also change. For something whether ENSO would have the same impact, I'd have to think about that. We'd have to look at that to see. I mean, it is an interesting thing. Like, how robust are these things when you go back when you don't have that information? That's a very important point.
Hi everybody, so today I'm going to talk about our work on tracing marine cryptotephras in the North Atlantic during the last glacial period. This was work conducted at Swansea University within the auspices of a larger project, the TRACE project. So just an introduction, what we're working on is the technique of tephrochronology. Everybody's been talking about volcanic aerosols in the first few talks, but we're interested in the ash particles from these eruptions. They're injected into the atmosphere and deposited in various areas around and far from the volcano. We assume this deposition is rapid, so geologically instantaneous, and this means if you can trace the deposits from an eruption, this tephra, between different records, they can act as isochrons, because they have the same timing of deposition. And that means you can use them as really nice markers, because you can transfer an age, if you have it in one record, to all other occurrences of that tephra. To do correlation, geochemical analysis of the volcanic glass underpins that correlation. But it's also really useful in ascribing this tephra to a source, and you can say where the eruption came from. That's quite useful in the context of the ice cores. You could say where the sulfate peaks, which eruptions deposited the sulfate peaks. What we're very interested is cryptotephra. So these are layers of volcanic ash that are not visible to the naked eye on core inspection. So when you get your ice core, your marine core, your lake core, you can't see a visible trace of the deposition of ash. So it makes it quite hard to identify these eruptions. We've developed methodologies to actually pick out these cryptotephras. The recognition of these cryptotephras has really increased the scope of tephra dramatically in recent times. So tephras are now being traced thousands, up to 8,000 to 10,000 kilometres away from the volcanic source. Why are we interested in looking in the North Atlantic? During this period, paleoclimatic archives record numerous abrupt climate changes, the Danskerd-Erskine events. Questions we're trying to answer are, were there leads and lags between these events? Can you see differences in the oceanic records and the atmospheric records? And can that help tell what drove these events? To achieve this, we want to try and more precisely synchronize the records by tracing cryptotephras between the Greenland ice cores and these marine records to act as isochrons, tying the records. And so you're not using climatic synchronization to inspect these differences. So that will be talked about Shuan as a poster in the session, talking a bit more about that work on synchronization. But what I want to talk about today is developing a framework of marine tephra horizons. This is required. The North Atlantic has often been overlooked, and there hasn't been so much work on tracing tephras in these records. So what we did within the auspices of the project is we had a really widespread core network covering all of the North Atlantic to try and pick up different sites around from Iceland, the main volcanic source of ash, and to look at different deposition environments and do we find different tephras, different records. We isolated records, well-developed proxy records. If we want to make these climatic comparisons, you want to have nice proxy records to be able to compare to the proxy records from the ice cores. Within the cryptotephra framework, what we want to define is the stratigraphic position of the tephras within these records and their relativeness position compared to the proxy records, and also have geochemical characterizations, really robust characterizations that people can then try and tie into in the future. It's a bit complicated trying to find cryptotephras in North Atlantic marine sediments, though. It's not a really nice system for it. What you really want is a volcanic eruption, primary tephra on the sea surface, rapid transport through the ocean column, and then sealed in within the oceanic sediments for then us to find in cores. There are some complicating factors in the glacial period. Firstly, tephra can be deposited on sea ice around Iceland and then rafted around the area. This can extend the distribution of tephra. We try and identify these types of deposits by looking at shard size variations. However, we don't think this imparts a very significant temporal delay. What's more worrying is when tephra is deposited on the ice sheet, icebergs carve off, and that can actually occur thousands of years after the actual eruption. So there's a temporal delay between the primary airfall, deposition on the ice sheet, before it's transported to the seabed. To try and look into that, we look at geochemical heterogeneity. Do you, in these deposits, see different tephra from different volcanic eruptions? And also looking at covariance with iceberg-rafted debris proxies. Another problem is that the seabed isn't just a nice flat surface with deposition occurring afterwards. You have problems of bioturbation, sedimentary loading when the tephra is deposited, and then subsequently bottom current redistribution and reworking of tephras. And this can affect the stratigraphic integrity of the deposit, essentially blurring where ash particles are in the sequence, and can affect the definition of the isochron position. So to tackle that, we do very high resolution shard counts to see where peaks in concentration are, and then rigorous geochemistry through long profiles to see if different eruptions are preserved. So to this end, we've developed methodologies to try and pick out those processes. The prior North Atlantic approach has often been focused on very visible tephras, but also the coarse fraction. People would be sieving material for 4-ram analysis and find tephra in those records. We've adapted an approach from terrestrial studies. It's also been previously applied to some other marine cryptotephras to look at finer material and finer fractions. So the process we go through, first we do carbonate removal to get rid of those 4-rams. All of this process is trying to isolate the tephra from the host sediments. We do sieving to isolate grain size fractions where you think tephra should reside. Density separation with heavy liquids helps us identify rhyolitic shards. This is what we're essentially looking for in sequences. This is silica-rich, lighter material identified from Iceland, and you can see they're very small particles, 50 microns in diameter. Unfortunately, basaltic tephra, which is also very common from Iceland, this iron-rich browner material, has the same density as quartz, which is the main constituent of the oceanic records, but we can use magnetic separation to exploit magnetic properties of basaltic tephra and separate it from the quartz. Do optical identification, essentially mounting up these on microscopic microscope slides and count how many shards are present to create these concentration profiles. Once we've found peaks, we then pick out material for geochemical analysis and do an awful lot of analyses from deposits. So just to quickly run through that process as an example, this is one of the cores we've worked on from the Goeben Spur. We have a nice proxy records from this core showing those downscaled Erskine variations. Firstly, we look at a 5 centimetre resolution to see the presence of tephra. So this is this brown basaltic tephra. We can see peaks in the record and then peaks in the rhyolitic tephra. 1 centimetre resolution counts allows us to further refine the position of the stratigraphic position of the tephras. And then peaks are isolated for geochemical analysis. So we have these for all of the different records within our network. However, what we want to think about is, do we see common deposit types that can tell us something about the transport processes? So analysing all of the records we have, we've isolated different deposit types. Firstly, we have these kind of Type 1 deposits, they have low shard concentrations, very discrete peaks, often within 1 centimetre. They have homogeneous geochemical compositions. This is kind of a plot of aluminium concentrations versus titanium concentrations, very tight populations, which we can link to single volcanic sources from Iceland, but also so they're most likely to be single volcanic events, primary airfield deposition, and isochrons. Have these type 2 deposits, similar in form, having distinct peaks, but they have higher concentrations. This means we see the trace of bioturbative reworking. You can see ones that are homogeneous in composition, so these blue diamonds here have a quite constrained composition, but others are quite heterogeneous, these purple diamonds. And so analysis of geochemistry, the shard size, and relationships to IRD are necessary to determine if these were primary airfield deposits or ice-rafted deposits. Then we have these kind of type 3 deposits. These have a very flat bottom profile, very high concentrations. I think there's suppression of downward bioturbation caused by these events. They often have a homogeneous composition, and they're useful isochronous markers. What we can also see is sometimes these kind of type 4 deposits, they're quite prevalent. They have high shard concentrations, multiple peaks in concentration. Often they have quite heterogeneous geochemical composition, and that can be consistent between the peaks. And this is an example where you see individual deposits, quite a wide range, and can be linked to different volcanic sources. These are a bit more enigmatic, that they could be caused by iceberg rafting, transporting material from multiple eruptions, or what you might find is multiple closely timed deposits are actually being kind of constrained. The low resolution in the marine sea setting means we can't pick them out stratigraphically. And these are not really useful as high precision markers. So thinking of all the different cores we have in our network, you can look at are different cores deposited by different types of tephra and thus are more likely to preserve these isochronous deposits that we're interested for correlation. So develop this kind of traffic light system where you find some settings are deposited by nice isochronous deposits, these type 1s, and then we get some that just have single useful markers, some that show a mix of deposit types, and then some that show just not useful deposits, and some have no tephra at all. Looking at controls on this deposition, what we feel is that at these sites, atmospheric dispersal patterns are useful. You'd mainly get transport from the east to the south, and these could be isolated from iceberg rafting. At these orange sites, atmospheric dispersal is quite a good key control, but also they're proximal to LGM ice sheets. These are more complex sequences where you get the controls can be spatially and temporally variable. They're in a region where you should get iceberg and sea ice rafting. Atmospheric dispersal patterns can have an influence, but also they're lower sedimentation rates, so you might get more of that constrained deposition. And then these other sites we feel are much more affected by iceberg rafting, so they aren't really useful sites for tracking isochronous deposits. So what we've done, again, we've identified those deposits, we've assessed them, and what can be isochronous deposits. There's quite a lot of information here. So this is tephras found in previous work, and these are the cores within our network. Grey lines are tephras we feel are isochronous, but can only be found in single deposits, and then the coloured lines show deposits that can be traced between different records. So we've ruled through this work we can add 11 new isochronous deposits to the 3 previously known deposits. Unfortunately, many are single core occurrences at the moment, so it'd be good to trace these in further records. Some records, those type 2 deposits, which sometimes have heterogeneous chemistry, we can identify significant geochemical populations, but it'd be interesting to further explore those to see if it was caused by iceberg rafting or closely spaced deposition eruptions. Some other quick highlights from this. The majority of the horizons we found were of a basaltic composition, but from multiple Icelandic sources. There's compositional similarities between them, but robust geochemical characterizations helps us to assess correlations. Compared to the ice core records that Anna will talk about next, it's an order of magnitude fewer. We're finding 10 horizons and they're finding 100 or so horizons. But there is a consistency in the volcanic history. Older horizons are mainly from the Grimsvötn volcanic source, younger horizons from Katra and Hekla, which suggests that volcanic history from the marine records is similar to the Greenland records, which gives more weight to them being isochronous deposits. But one useful rhyolitic deposit is the North Atlantic ash zone 2. This has been known about since the 1940s. It's a really widespread and useful isochron for assessing cooling around GI 15. So very quickly to summarise, with our methods, numerous cryptotephras can be found in North Atlantic machine records. We really feel assessing integrity is critical to whether to work out if a deposit is isochronous, and you can find deposit types with common characteristics showing common processes. The spatial and temporal controls on the preservation of these isochronous horizons have been identified and hopefully will allow us to identify key target areas for future studies. And these horizons now form a framework that we can use to facilitate correlations to Greenland ice cores, and that work is ongoing at present. Thank you very much.
Do these only work with Icelandic eruptions in that you're just looking at the ash layer?
The deposit types we've identified.
In the sediment cores, in that you're just looking at an ash layer maybe rather than a chemical signature?
Yeah, we're just looking for the ash layer. We can't, at the moment, use other records to pick out where the ash layers might be present.
Yeah, I'm
in
just
the
thinking
cores.
about these stratospheric eruptions that we talked about.
Okay, yeah, no, I think at the moment this is very much focused on the Icelandic one. It could be possible that the tephra is present, and one of the problems we have, things like the North American ones, we found Pacific Arc tephras in the ice cores, they'd be very low concentrations, so they could actually get lost, essentially, in the background of Icelandic material.
Yeah.
Here we very much focus on looking at multiple cores and building up a really big network over in the North Atlantic. So look at that 5 centimetre resolution, you might lose peaks that could be related to more far-travelled eruptions. So now knowing target periods and target cores, we could actually go back and essentially do all cores at 1 centimetre resolution, but we were trying to build up a big picture for the minute. So they could be there, but they're much harder to find in marine records than, say, in ice core records, in terms of methods.
Thank you very much. So I'm going to move on from what Peter was discussing, looking at the tephra record in the North Atlantic, to look at our Greenland ice core tephra record. We've heard a lot about the ice core records of volcanic eruptions using sulfate records, but I'm going to focus on the actual volcanic ash that we find present in Greenland and look at this to give us some kind of an insight into the Icelandic eruptive history, focusing particularly in the period of the last glacial between 25 and 50,000 years ago. And this is work that was undertaken as part of the ERC TRACE project at Swansea University and in collaboration with numerous colleagues at the Centre for Ice and Climate in Copenhagen. So there's been a long history of searching for tephra layers and volcanic ash in Greenland, starting in the 90s, looking mainly for large, well-known eruptions that were based on the visual identification of ice core of tephra layers in the ice when the ice cores were being split or sampled for other reasons. This led to the identification of 3 very widespread eruptions, all from Iceland, that were present in the North Atlantic and also in Northwest Europe. In moving into kind of the early 2000s, the sampling for volcanic ash layers moved to looking at records of chemical signals of volcanism within the ice, and therefore a direct search for any volcanic ash associated with this. And you can see that this increased the number of tephra layers fairly significantly. So where a significant sulfate spike was identified in the core, areas around that would have been directly sampled for volcanic ash. And often that did lead to the identification of tephra layers. However, as this work continued, we found that maybe you would be sampling some of these larger sulfate spikes in the areas around them for tephra. You'd find no tephra or ash associated with some of the indicators, but tephra somewhere else in the bag or very close to those large sulfate spikes that may be associated with a very smaller signal, chemical signal, but wasn't kind of the initial intended target. And we were also so increasingly finding the presence of volcanic ash without a significant chemical signal. So when the TRACE project started, we decided to begin a more intensive search for tephra between most of the last glacial period, so between 10 and 120,000 years ago. And this vastly increased the number of ash layers
that we found. So we have so far recognised over 300 tephra deposits, and these are predominantly cryptotephra layers, so as Peter already explained, these are tephra layers that aren't visible in the ice or whatever sediment you're looking for them in. And so you just have to look for them by searching for fairly low concentrations of this volcanic glass. And we've done this and identified over 300 deposits from the North Grip Neem and the Grip ice core records. And most of these aren't really associated with any chemical signal of volcanism. This has been achieved by using much wider sampling windows. So the green areas highlighted in this figure show the areas of North Grip that have been sampled for their tephra content. So this is direct sampling of ice, spending quite a lot of time in Copenhagen's freezer, cutting off the very edge of the ice cores that no one else is that interested in. But we have therefore sampled significant parts of North Grip, and in particular this time period between 50,000 and 25,000 years has been sampled in its entirety. So we know that we've discovered any tephra there to be found, so we can start to use this to look start to make some kind of inferences about what this is telling us about the type and number of eruptions present. We see a lot of tephra layers in the younger part of the record. As we go back in time, maybe from around 120,000 to 80,000 years, and we see a lot fewer tephra layers present, despite fairly extensive sampling. We're not really sure why that is, possibly due to the thinning of the ice itself, meaning that we aren't actually looking at a great enough volume of material. So once we've found these tephra layers, we have to try and work out where they're from. That's why the volcanic ash content of the ice cores is really important. It lets us know where these eruptions can be sourced from. The vast majority of our tephra layers do appear to come from Iceland, and we undertake that major element geochemistry that Peter described. And we can use various pi plots. This is looking at silica and the iron-titanium ratio. And using previous proximal information from Iceland itself, we can plot our data against fields of Icelandic volcanism. So this is looking only at basaltic tephra layers. And we can do this going through the whole record and ascribe each of our different tephra layers to a volcanic source. So you can hopefully see that this darker, thicker envelope here, this is tephra layer from the Grimsvötn volcano. And this is present throughout our record in each time slice that we look at, and really dominates the Greenland tephra framework. In the younger time period, similar to what Peter described, we see a lot more tephra layers from the Katla volcanic system. There are some of these present as we go back in time, but really dominant in this younger 25 to 32,000 year period. And this is also really the only time period where we see tephra layers from Vedervötn and some from Hekla and the Kverkvoll systems. But as we move back in time, we are definitely focusing on a number of Grimsvötn eruptions. So this lets us characterize the volcanic source of the tephra layers we have. And that's great, and that's fine if we're looking at Icelandic volcanic history, as I'm going to make some inferences into today. When we want to go further and try and make some of these correlations with the North Atlantic record, we are sometimes hampered by the fact that these geochemical signatures repeat. So these are our tephra layers from Katla. They're very difficult to distinguish on major elements alone, and actually they're also very similar when we look at their trace element composition as well. When we look at the tephra layers from Greenland, even though initially they may look very similar geochemically, they can be separated by very small variations in their titanium concentration, allowing us to distinguish between them and making them more useful for correlation to wider records. These geochemical similarities make correlation to other lower resolution records challenging. We know that these are discrete events in the ice cores, but the ice cores are really high resolution. And when we look at trying to compare these to marine records, such as the ones Peter was talking about, we may be picking up a number of these eruptions closely spaced in time as one eruption in a marine core. So this repeating geochemistry does make this more challenging. But to assess the volcanic frequency, we only really require the source. Because we can also use the geochemical characterization to match tephra layers between ice cores. And we've done this throughout the glacial period to support the GICCO5 timescale transfer from North Grip to Neem and from North Grip to Grip. So locating tephra layers in the 3 ice cores that have the same geochemical signature and then the same age, and using this to test the matching based on the chemostratigraphic match points. So this has worked successfully in all cases. If we want to look at a record of Icelandic volcanism, we can't really turn to the proximal records on Iceland because any volcanism from the last glacial period isn't really preserved or available. So it's therefore likely that Greenland offers the best opportunity to investigate Icelandic volcanic history. It's by no means going to represent a complete volcanic history, but it will be one of the most complete, I think, available. So all of the tephra layers, apart from these 16 highlighted in blue, are from Iceland. These are more far-travelled eruptions from Pacific arc volcanoes. But we can leave those aside for now and just focus on our Icelandic eruptions. And particularly this time period from 25 to 50,000 years, because this is where North Grip has been sampled continuously, so we know we're not missing any eruptions. And in this time period, we have identified 74 tephra layers in North Grip, 22 in Neem, although we have to remember that Neem hasn't been completely sampled. Only 7 of the eruptions in Neem appear to be unique events. The rest all correlate with a tephra layer in North Grip. And then another 22 tephra layers in Grip, 13 of which don't correlate with another ice core. So that gives us a total of 94 unique events within this 25 to 50,000 year time period. And we can look at the frequency of these frequency of the ashfall events going back in time. So we have North Grip in blue, Neem in purple with the gaps where we haven't done any sampling, and Grip in green. And this is related to the oxygen isotope record from North Grip, and the vertical lines are marking the peak of the shift to the interstadial. We can see a number of increases in the frequency that occur and generally seem to correspond to interstadial warming. So we have the first one back at around 48,000 years, seeming to correspond with the warming into interstadial 12. This dramatic increase in ashfall events associated with interstadial 8 that can also be picked up in Neem and Grip. And then other maybe less obvious times, such as this with this increase associated with interstadial 4. So in all cases where we see this kind of increase in frequency, it seems to be corresponding to interstadial warming. And it's previously been suggested that there has been an increase in Icelandic volcanism after the deglaciation due to the rapid melting of the ice sheet. But it seems that we may be seeing a similar signal as we go into interstadial warming, and maybe changes to the ice sheet over Iceland were affecting the volcanism, which maybe isn't a surprise, but it certainly seems to be supporting that. And we need to look into that a little bit more to try and work out exactly why we see this pattern. We can split, just for the North Grip tephra layers, it down based on the volcanic system. And again, we've seen and have said that the record from Grimsvötn really dominates in the earlier kind of 15,000 years. And here we see, again, some of the increases associated with the warming. And we can see really that after we stop getting many Grimsvötn eruptions, that the Kverkvoll and Katla system really take off and then start to increase. So maybe something there going on about different parts of the different volcanic systems operating at different time periods. We know that later in time, Grimsvötn does become more active again. So just to summarise, we have looked at the development of a Greenlandic volcanic event stratigraphy, and we have a large number of basaltic tephra layers present. So most of the 300 are basaltic. There are about 50 silicic Icelandic eruptions, and then those 16 far-travelled layers from the Pacific. Between 25 and 50,000 years, we see 94 unique Icelandic events. And that early period is dominated by Grimsvötn volcanism. But we see a step change increase in frequency of eruptions, which are associated with those stadial-interstadial transitions, particularly on the interstadial warming, suggesting maybe that there's retreat of the ice sheet due to warming, which is leading to tectonic movements and associated increases in volcanism. Thank you very much.
Okay, so thank you for having me in this session. So I'm going to say a few words about VOLMIP, which is a CNRS 6 endorsed activity co-chaired by Davide Zonchetin, Claudia Timmreck, and myself, and which aims at increasing comparability of results across different climate models to better understand the effects of volcanic eruptions on climate. So this initiative stemmed from the main conclusion of the last IPCC report, which recognized and identified the volcanic forcing as the main source of externally forced climate variability. So the relative forcing due to volcanic eruption itself is short-lived and lasts about 2 years after a volcanic event, but its influence on climate can extend a longer time scale through the long memory of ocean heat content. However, from this conclusion, uncertainties and knowledge gaps are still very large, mostly because we have very few observed events over the historical period, and these events have a relatively small amplitude, which makes it difficult to disentangle its influence on global temperature, either the land or the ocean, since the magnitude of the signal is about the same size as the amplitude of the noise of internal variability. And this lack of observation also leads to large uncertainty in the radiative forcing in the CNRS 5 simulation over the historical period, especially around large events. And this type of uncertainty could be related to the volcanic forcing dataset used in the model, but also to the strategy of implementation of this forcing in various models within the CNRS 5 exercise. And this type of uncertainty increases and grows larger for events of the remote past. For example, here for the 19th century, with the two large eruptions that occurred, Tambora in 1815 and the one that is unknown just before in 1810. And we can see here that the top of the atmosphere net radiation balance and the northern hemisphere temperature response simulated by PME3 model for the last millennium show large differences. Again, these differences are probably related to uncertainty in the forcing reconstructions. As described by Matthew earlier, these forcing datasets have strong assumptions behind them, which might explain the differences in the forcing itself, but also we don't really know how this forcing has been implemented in the models, which might explain in the end the large spread among PME3 model regarding the influence of this large eruption on climate. Another point I want to stress here in this slide that is extracted from a paper by Zonchetin et al. In 2015 is that this could be the reason of the large differences among models. However, if we compare the spread here in northern hemisphere temperature among PME3 model to the spread from a large ensemble run with one single model, we can see that they are very much comparable, which stress that the role of internal variability is very important in modulating the climatic response to a large volcanic eruption. And we need to consider both issues. VOLMIP aims at tackling those uncertainty by constraining the forcing dataset used in models and their implementation strategy in order to better evaluate the radiative forcing simulated by models and the climatic impact of this eruption on climate. So I won't describe the full experiments data we identify with VOLMIP, but the details can be found in the publication that was published last year, in summer last year in GMD. But the general philosophy we choose to tackle was to define two sets of sensitivity experiments. A first set that was designed to allow disentangling the dynamical response to a volcanic eruption on the short term, like a few years, for a Pinatubo eruption. And the second set of sensitivity experiments aims at exploring long-term response on decadal scale for eruptions that have a higher signal-to-noise ratio, which means that are stronger, such as Tambora in the tropics or Laki in extratropic, for a single event or for a cluster event, such as in the 19th century. So for the short-term dynamical response, our experimental protocol will allow to address one of the most emblematic issues regarding the multimodal semi-5 skills in reproducing the stronger polar vortex after El Chichón and Pinatubo eruption, the positive phase of the North Atlantic oscillation, or even the winter warming. The last IPCC report showed that the semi-5 model failed in reproducing these main characteristics, and we don't really know why. They also tend to overestimate the tropospheric cooling as compared to reanalysis, for example, here. So our experiment will allow to increase comparability among model results and identify the dynamics behind this kind of processes. This also applies for the El Niño Southern Oscillation. Here I've just presented the results of two large ensembles run with two different coupled ocean atmospheric climate model for a Pinatubo-like eruption. And we can see that in one set of experiments, La Niña-like cooling is simulated over equatorial Pacific within the year of the eruption, while this large ensemble run with another model instead shows an El Niño-like type of response. And these differences could be due to, in fact, an overestimated tropospheric cooling, which might hide a dynamical response that is consistent across model. And that's what we've tried to explore in a recent study where we removed the mean tropical cooling to isolate the intrinsic ENSO response among semi-5 models. And when we do so, we show that the percentage of model showing an El Niño event after the 5 largest tropical eruptions of the historical periods increases by about 30 to 60% as compared to a background probability of El Niño event in those models. So this suggests that there is a tendency for an El Niño event to appear after a large tropical eruption, and in our model, in the IPSL model, we identify the processes at play, which in fact involve a reduction of the West African monsoon, the year of the eruption, which initiates an atmospheric Kelvin wave following a Matsuno-Gill type response, which quickly, like a few months after the eruption, induce a westerly wind anomaly in Western Pacific, and then trigger a response over the ocean, equatorial Pacific, with ocean Kelvin wave, and this trigger the full feedbacks associated to a natural development of an El Niño event, such as the Bjerknes feedback. So this is a result from one model, but VOLMIP will allow evaluate the robustness of this kind of mechanism across different physics of models. Concerning the long-term dynamical response, there are also large uncertainty at decadal scale. One of the most well-known uncertainty concerns the response of the AMOC to a volcanic eruption. In general, semi-5 models show an increase of the AMOC strength after volcanic eruption of the last millennium. However, the magnitude of the increase varies considerably from one model to another. So there's still we don't really know why there are such large differences. This could be due to the ocean preconditioning, as shown in this slide. We can see here that the AMOC response following the eruption depends largely on the ocean preconditioning before the eruption, which means that the long memory of the ocean can strongly modulate the climate response at decadal scale after the eruption. This could be also due to the strength of the eruption, such as shown in this study. For a relatively weak eruption, there is a strong strengthening of the AMOC, while when the eruption magnitude is stronger, the response is more like is less clear and rather suggests sometimes a weakening after at least a decade. So to summarize, VOLMIP has defined a protocol that will rely on prescribed aerosol optical property for Pinatubo eruption that are consistent with CMIP6 forcing data set, and for this for Pinatubo eruption, and also volcanic forcing data set that are consistent with PMIP3, last millennium forcing data set for the 19th century. We also design ensemble experiments that sample the natural range of the internal mode of variability, sampled either within a pre-industrial control run or sampled in the last millennium simulation, depending on the experiments. So far, more than 11 groups have committed to perform VOLMIP experiment, and more detail can be found on the website here. And I'm going to conclude quickly here with the fact that this activity has been coordinated with other groups, such as CIRC and PAGES, which PAGES VICS activity, which separately tackles several levels of uncertainty. CIRC will concentrate on the global aerosol intercomparison of the formation of volcanic aerosol in the stratosphere and their evolution, while VICS will focus mostly on the impact on society and climate. And I'm going to stop there. Thank you.
I wanted to say that the Driscoll et al. Results you showed, I think we figured out the problem. They looked at a lot of small eruptions, and they looked at 2 years after instead of 1 year after the eruption. And so the paper that Zambri and I did last year showed that you really do get a robust result. And
Yep.
second, I really like your cool animated GIFs for the volcanoes. I'd like to get a copy of those.
And to add on Anne's comment concerning the robust signal of the CMIP5 models with respect to northern hemisphere winter response in northern hemisphere winter, we also did a study with the MPI-ESM model, and my colleague Matthias showed that this is a factor of two things, so that you need that the strength of the eruption plays a really important role, and also the number of ensembles, because we have a really high interannual variability in northern hemisphere, high latitudes in winter, and this one has to take into account, and you need a strong forcing response. So.
Yeah, that's true. That's why we defined a large ensemble to better detect the signal over the noise.
First of all, I would like to thank the organizers to give me the opportunity to present here this very new study. And also I would like to acknowledge my co-workers, in particular Matt and Davide, who has also contributed a lot to this effort. Okay, so I'm a little bit embarrassed to show you this figure again, but if you don't take anything from this session, you will probably remember this figure. This shows the northern hemisphere temperature response with PMIP3 models compared to reconstruction, and it should highlight a little bit that there is a large uncertainty range for the early 19th century, not only with respect to the reconstruction, where there's also some improvements, or there are not some improvement, a lot of improvements I heard yesterday, but also with respect to all the climate models or PMIP3 models who take part into this. And the colored lines just indicate different models. So then when we look a little bit closer to it, and Myriam just already mentioned this point or tackled it, we have here a range of uncertainties, and this could have mostly 4 different reasons. One, of course, that we have an intermodal spread. Every model behaves differently and has its own errors or
advantages. And then we, of course, have uncertainties with respect to forcing, with respect to forcing. So we have just already saw that in PMIP last time there were actually 2 data sets recommended, the GAO one and the Crowley one. And okay, available. So sorry, I have to be careful. So they were recommended. It's the same now with CMIP6. They're only recommended and available. Okay. Yeah, now I'm a little bit confused. But in CMIP6 they're recommended. Okay, so and then there were implemented in the different models, and as you can see here in the clear sky net flux radiative anomalies, we see differences about a couple of watt per square meters, just due to the different implementation and treatment of the forcing data sets in the model. And last but not least, this is to highlight it with our model, the MPI model, that we have, of course, interannual variability, and it depends really on which state of the ocean you set up your model runs, and they develop in different phases. So we have a lot of uncertainty, and as Myriam just highlighted, we had this WARMIP intercomparison, and with this really essential and crucial thing that we would like to have consensus forcing input data for the studies we propose in WARMIP. So if you take another forcing data set, you are out of WARMIP. You can do it, no matter, it might be good, but it's not a part then of WARMIP. So WARMIP will reduce these uncertainties and just focus on the interannual internal variability and on the different model spread. So we have some residuum to leave out. We have, of course, volcanic forcing uncertainties. This is not something what WARMIP tackled, but we've, of course, as Matt has shown in the first talk of today's session, which are there. So in WARMIP, we decided for the early 19th century to use the Evolve 2K data set, and this is also, can I now say, recommended data set for PMIP, Gavin? Okay, but it will be also, of course, it's in this paper from Johan, it will be also, I think it's a recommended data set for PMIP. And what you can see here is a comparison for the early 19th century from the between Crowley, and Crowley-Untermann, and Evolve 2K, and we see that, for instance, the Tambora, the peak forcing for Tambora is smaller, as Matt already mentioned. And he just also thought that there are uncertainties, so we now have some information about uncertainty of the sulfur emissions, also the uncertainties derived from ice core, which are for the larger ones around 20%, and for the smaller ones are even larger. So this is something what might be interesting to look at, how would be the differences in the climate response if we take into account this uncertainty. And the approach we are doing, or we have started now, is that we perform 2 sensitivity runs with volcanic forcing estimates with 2 plus minus 2 sigma of the retrieved SO2 emissions. And here you see in the panel, you see with the dashed lines the high and the low scenario. And interestingly, for the high scenario, our peak forcing, our peak AOD is similar to Crowley and Untermann. So we also have then somehow easy comparison. So which model we are using? We are using the MPI-ASM, and you needn't to capture everything, but this is a coupled model. We have an atmosphere model, the SIECA model, we have an ocean model, and we have also land and marine biogeochemistry. So it's an Earth system model, as many are around nowadays. And we will use with this model, we have performed 3 experiments for the mid, which is the standard, the recommended Evolve 2K forcing set, and a high plus 2 sigma and a low minus 2 sigma forcing scenarios.
And for each of this scenario, we run 10 realizations. And here I just want to show you, or to give you a flavor, how we set up the model runs. What you can see here is the AMOC in the control run. It's a 1,500 years control, no, 1,300 year control run with our model. And we randomly set up every 100 to 200 year, we use an initial starting date. So these are indicated here with the blue files. So we don't care about, we just say 100 years, or maybe sometimes 200 years, and these are our initial conditions. And then we started to do the runs. And here you see the first thing, of course, is to look into the fossil influxes. Here we see the top of the atmosphere. It's called TORs, shortwave fluxes, so the solar input thing for the three scenarios. And just to give a little bit of information about the nomenclature, which will come up for the other plots as well. Of red is this low one, blue the mid, black the high scenario. In green, this green line, I don't know if you see it in the back here, it's very small green lines. This indicates the range of the control run, of the 1,000-year control run, the 5 to 95% percentile of the control run. And below, you find the rectangles indicate when the scenario or the experiment is significantly different from the others. So just to give you also an idea when it's when it's different, and positive anomalies are indicated a downward flux. Okay, so this is the shortwave, and of course, when we look to the net radiative fluxes, we see similar things. And what's also interesting is, and here's the outgoing long wave radiation and below, but what we see here already quite nicely is that the distance between the mid and the low scenario is much larger between the high and the mid scenario, due to the fact that aerosols, or the radiative effects of the aerosol, are not linear. You cannot really scale it. So then the things come up that larger particles don't scatter so efficiently and absorb more. So this is this effect which we see here quite nicely. Now the temperature. Okay, here we have global surface air temperature anomalies, and we see similar things as we have seen before. So we see in particular that the low scenario here, the red line, is much lower than the other lines, and show a modest temperature response, which is more in line with what we know from proxy reconstructions of this period from ocean and from land. And we also see, what I find quite interesting here as well, is that only in the low scenario, is the pointer here? I don't know what I mean. Yeah, just look to the magenta line, 1850. We see that only the red scenario, or the ensemble average of the red scenario, they're in the range of the control run again. So the others are still lower. So when we set up, or no, not when we set up, when nature set up the Tambora, when the Tambora volcano started, our climate system was not back in equilibrium again. It was still colder than before. So, according to our simulations, and we also see, this is also a quite nice thing, that the recovery of the surface temperature anomalies after the Tambora eruption takes a really, really long time, and much longer than we see after the 1809. So, what did I do here? Help. I don't know what I did. So I just can confirm. Okay, so here just we saw also the thing. How many? 2? Oh, okay,
So you see Northern Hemisphere, of course, is much higher. So we just go then directly skip into the temperature anomalies, so the pattern. And you can see here the largest anomalies. This is the ensemble average for the year without summer. You see the largest temperature anomalies occur over the tropical Northern Hemisphere land masses. And stippling points here indicate which are not significant. And of course, and I have to apologize a little bit because the temperature anomaly spread is quite, shading is quite large. So plus minus 1 Kelvin is still here white. So, and 1 to 2 is green. So below minus 2 Kelvin anomalies, they are here indicated in blue, just to give you also in the back a flavor about the strength of the. Here we just see the differences between high and low, and we see that in the low scenario we don't have the most parts not go under minus 2 Kelvin. So only a very few spots. So, but this is what I will say. This is the ensemble averaged over 10 members. And here's the comparison now. What we already saw in the figure before, as you expected, the low scenario with the modest temperature response fits with our model best with this reconstruction average. It might change, and but this is just the present status. And just briefly to the precip. Here we see this of what we know. Almost that the most precipitation anomalies occur in the tropical region. We see partly a shift from the ITCZ, and we see also that, in particular, the warm pool region, the maritime continent, is affected by the volcanic forcing. And here we see also the differences between the three scenarios, and it's really astonishing that, in particular in the tropical Pacific, we see quite substantial differences between the three experiments, and we will have to look into it a little bit further in the next time. So, coming to my summary, our model is with the evolve2K date volcanic forcing series. This is also good to know in the ballpark of what we already know or have experience with previous studies. We see that, in particular, the lower scenario is quite, the climate response is quite sensitive to the lower bound of the forcing. And we see also a lot of interesting patterns which we now have to further earn and also compare it with new temperature reconstructions. We heard yesterday a couple of them. Thank you very much.
Thank you very much to the organizing committee for inviting me, and and for adopting me in this session. I'm really very excited to be able to show you the preliminary data from Puerto Rico and previous data from Mesoamerica. It's fascinating to me how two lonely stalagmites and caves are responding to natural forcing, particularly volcanic forcing. And before I go on, I'd like to thank all my collaborators. And there are too many to go through, but especially Davide Zancatin. And also, this is Rolf, our PhD student who's done most of the work. He should actually be giving the talk. And right now he's in Cueva Larga, and he's looking at a ghost, apparently. And he's been in this cave. He goes this is one of the longest monitored caves. We started in, I think, 2011, and he goes there every month. And so this is a very important part of understanding speleotherm growth, is to understand how the signal perpetrates through the cave. Of course, we all know, most of you know about speleotherms, or how important they are becoming. The primary thing is that you can really get fantastic dates on them, plus or minus 1 to 3 years, back 10,000 years if you have the right material. And of course, these are just points in time, but eventually people are working on laser ablation, ICP-MS, and I'm sure in 10 years they'll be scanning down a speleotherm and getting continuous dates because they are developing these things. So technology is going to help us quite a bit. And of course, stalagmites, which we use, go back, you can go back 1 million years at seasonal resolution if you have the manpower and the money. And of course, many stalagmites don't grow continuously, but there are a few. So we've been looking at cave processes in Puerto Rico, and one of the most important things we notice is ventilation, so that at the bottom you can get the outgassing of the carbonate material. So you have to have a negative pressure in the cave to do that. And Rolf has written about, we have written 3 papers now on these findings of cave processes. One of the most important aspects is the amount effect, which basically works in the tropics, where there's a direct relationship between the isotopes, which we measure, and the amount of rainfall. So the more rain, the lighter the isotopes in the speleotherm. And thus we can use it to reconstruct the hydrological cycle quite well. So these are data that we measured in Puerto Rico, but there are many, many articles on this fact, and we think this is the main contributor. There are others, of course, like the source effect and also temperature. So these are the 2 cave locations. One is Xibalba Cave, which is we got in, I think, 2009. That was by Thomas Miller. And Cuerva Larga, where Rolf worked. Our work in Xibalba Cave was published previously, but it's the Cuerva Larga cave results which I'd like to show you primarily. But first, the Xibalba Cave of 2007, it is in the Belize-Guatemala border. It hasn't been monitored very well, but I just wanted to show you pretty much where it is. The main thing is it's not open to the general public, so no pollution of the atmosphere. This is the Xibalba Cave. This is our beautiful ragonite speleotherm, which we obtained at that time. It has hardly any detrital thorium, so that's very important for the uranium-thorium series. And it has lots of dates. And I have seen people doing now every centimeter a date. So this is the fantastic thing about these. You can get a really great age model. And of course, we can mill them at microns. So our time resolution can be seasonal if you want to, but it of course depends on the cave processes. Because some caves take a while to mix the signal. The Puerto Rican cave is about 2 years. I'll show you that. But this is our age model for the Xibalba cave, and with that, we were able to reconstruct our data. But first, I wanted to show you the Cuerva Larga cave, where Rolf goes every month, and the thing is, it has mostly a constant temperature. The stalagmites are dripping actively, so we know that the top is the date of the top part, not open to the general public. And it's very important where you get the cave. This is in the deepest part of the cave. There's hardly any contamination, and according to our model, the calcium carbonate is precipitated in equilibrium. So this is a calcite stalagmite. The other one was an aragonite one. So this is Cuerva Larga, And of course, I don't want to go into this in depth because we have a number of papers, but you can see that the basic thing is that it's calcium carbonate appears to be in equilibrium with the drip water. And this is the Cueva Larga stalagmite. Okay, so the age model for the Cueva Larga stalagmite is, we have 4 points so far. That's why I'm saying it's preliminary. We're waiting for the next dates to come to us from Germany. Those are going to be another 8 dates, but we don't think that the conclusions are going to change very much. This is the record from the Xibalba cave. The oxygen isotopes that we measured from Mesoamerica. You can see there's a lot of work with the milling, huge amount of samples. And so here we have it according to depth, and we can convert it to age here, and run a smoothing average through the data. And so this is where we started about 4 years ago. We said, well, this is interesting because we can see Tambora. But first, this is precipitation. As you see, wet is on the top and dry on the bottom. So things were going fine, and Tambora came along. And then things started to dry out. Then Krakatoa came along, and there was a recovery period. I'll talk to you about that. And then again, Agung. So at each of these points, we saw a drying. And then we looked at it like this. We divided the period into clusters. So there's cluster 3, 2, and 1. And we have modeled forcing over here based on 3 different models. The CCSM4 seems to be the best. What's going on here is that you have the volcanic eruption, and you have the drying, and then the next one. So the cumulative forcing is very similar to the isotope record. In between clusters 1 and 2, there's little volcanic activity, and we have then a increase in precipitation, and then the next cluster occurs with the forcing. So this is what we're calling the persistent part. So it keeps on going down until there's no more volcanic forcing available, and the system sort of recovers, and then you have the next period, and I'm sure all of you know this by heart up here, and then it goes down again. Of course, here we have also a drying trend. So that was a problem with this one, but not with the next one, which I'd like to show you. What did I skip? Okay, so the question was, okay, then there should be other stalagmites which should show this type of record. And looking at the literature, I could find these others from Central America, but this is ours here, but this one doesn't have it because of the record, the age model. You have to have a really good age model to see what I'm showing you. Okay, so this is the record from Puerto Rico, and you can see a very nice, this is magnesium calcium and delta 18O. If the two are similar, then it shows you that we're having a really good record because there's no precalcite precipitation, PCP. These are not exactly the same, but you can see here, well, I learned yesterday there was a volcanic eruption in 1600 and 1695. This pretty much follows it. Maybe this is just slightly better than the oxygen isotope record. But here you see, this is a very similar thing that I showed you before. This is the record that was covered by the Mesoamerican one. Persistent decrease due to volcanic eruptions every time it goes up. A recovery in this phase. Then it goes down here, and then recovers, and then goes down over here. But this one extends back to 1400. So we think that the same thing is happening. This was a period of volcanic eruptions. Where you put these lines is sort of arbitrary at the moment, and we're going to get a better age control, but we think definitely that this a drying trend occurs, a persistent drying trend occurs, which you can see here specifically in this area, where each volcanic eruption causes a drying trend until there is a period of no eruptions and the rain starts to increase again. This is more rain, this is less rain. So over here, we've just put together, David and I were sitting in a restaurant and back of the envelope kind of thing about forcing, and you can see this sort of works pretty well here too. Of course, there are different forcing models and age models and whatever, but you can see here it goes down, down, over here. Here there's it's very similar in this part. This could be over here. And so, generally speaking, I think this will hold. That every time you have a volcanic eruption, that you have decreases in precipitation in Mesoamerica. And the question is, what is the intermediate process? And here, if you can see it, I've put on the AMO. Looks very similar to the last 150 years. So we think the AMO is the process whereby the signal is transmitted. When the AMO is high, the temperatures goes up and the precipitation goes up. So we have to look into this further, but there have been plenty of papers that I've been reading about how volcanoes affect the AMO through various processes. And look at the, if this could be used, for instance, if I were going to say something definitive, perhaps it would be that the volcanic eruptions are sort of forcing the AMO, but I don't want to go out on a limb, but that would be the interpretation. And this perhaps could then be an AMO signal. Certainly during the Little Ice Age, the AMO was very low and there was very little precipitation. And of course, Davide will do the modeling aspect of it, and I hope I've given you some food for thought. So that's it. Thank you very much.
What about the model generation of precipitation? Did you look at how these models calculate precipitation in Puerto Rico and compare that to your results?
I haven't done that yet.
I mean, you're speculating about mechanisms, but you have model runs. Why don't you just use what the model output is?
I'm not a modeler. I have, I'm a spiliotherm man. If you can give me your model, I'll be happy to do it. I think I've also noticed that the tree rings show very similar results. And when it's very cold, we have very little precipitation.
Well, actually, Amos, in the nature communication paper, we looked into the models, and precipitation in the simulations we looked at didn't show any of this signal.
Did not show.
No. None of the simulations. Yeah.
Okay, thank you, David. That's why I have David with me.